Hello everybody, welcome back to another stream where we talk about Quilibrium, L1 news, and then also dive into some development topics. As always, a disclaimer with our broadcasts, the discussion today is not a solicitation for investment and does not constitute financial advice. The QUIL and corresponding wrapped QUIL tokens discussed on this broadcast are utility tokens, and Quilibrium Inc. does not endorse or encourage engaging in speculation on the utility token of the network. As always, we start off with the mission. The mission of Quilibrium is to secure every bit of traffic on the internet, whether it's on Quilibrium itself, in service of other crypto protocols, or the broader web. Now, let's go ahead and set an agenda for today because, wow, what a crazy day it's been. To start things off, we'll go ahead and talk about some news. And then we'll dive into some QConsole stuff. First and foremost, news. Obviously, as a lot of people have noticed, the economy is absolutely bonkers right now. Both the traditional stock markets, both foreign, domestic, doesn't really matter. Everything's kind of going chaotic right now. One thing that's really important to understand, even when we're in situations that are basically situations that have never happened, it's important to keep in mind that no matter what, it's never as good as it seems, and it's also never as bad as it seems. Things always keep moving. And so just important to remember that as we continue to march forward. In the past, I've drawn some parallels to three major industry crashes. One I like to point to a lot, and I have a much broader talk about, it's on YouTube, is the hobby computer market and the similar nature it has to the current crypto market of today. But I've also drawn comparisons to the video game industry collapse in the 1980s and also the dot-com bust in the early 2000s. There are a lot of cases that history likes to repeat itself. And I'm going to remind folks of some of those cases real quick. The first, of course, is one of the most infamous. We have one of the largest industry titans out there today, Amazon. And in Amazon's early days, and this was during like the dot-com bust era, Bezos was taking this fledgling company and bringing it to newer heights and was doing reasonably well as a founder. But people who felt like they knew better than him kept telling him that the peak was in and he should sell now, that he should just sell to Barnes & Noble and call it a day. He didn't, and we now know Amazon to be an industry behemoth. Similarly, during the early days of the hobbyist compute era, there were two young, scrappy, hippie-looking individuals that wanted to bring personal computers into everyone's home. And investors just couldn't understand these people. They made all sorts of crazy comments about their appearance. They didn't believe it was even possible because what they knew as computers were just too industrial. And of course, that company was Apple. And last but not least, the game industry. In the 1980s, when the video game industry had collapsed, Atari was the previous titan that took the industry down with them, essentially. And nobody really expected that a company that was known mostly for its trading cards and some arcade cabinets was going to completely change the way that the gaming industry was from that point forward. And that was, of course, Nintendo. I draw these parallels because it's important to understand that during these types of turbulent times, these are the times that dynasties are made. And that's just something I encourage people to think about when we're obviously dealing with a situation as we're dealing with right now. Now, so for some happier news, 2.1. So like has been previously said, 2.1 is slated for the 14th at frame 244,200. Yeah, I always have to remind myself. Anyway, yes, 244,200 is the cutoff frame. It's looking like it's going to be more midday on the 14th now. It was originally slated for midnight, but obviously the network's frame rate is not consistently at at a stable rate, and so it's hard to guesstimate when that cutoff's actually going to land. But right now it looks like it's going to be the 14th midday. Last but not least, this is something that came up from the previous space, and I wanted to add some clarity to it because there was some confusion after it. There was a question where somebody asked what emissions are going to look like in 2.1, and I pointed out that the proof of meaningful work algorithm and the overall global state that we're going to be launching into 2.1 with is going to put it roughly at 102 QUIL per interval maximum. And somebody aptly noted that the current frame rate of the network and the current issuance rate per frame in conjunction with the new frame rate of 10 seconds and 102 QUIL per interval is actually roughly the same. And so what people were wondering about is how can I say that the issuance rate is actually going to be diminished? And the reason is because the nature of how proofs, and I've talked about this a number of times, and also there's an article that I've written out that explains the entire tokenomics of proof of meaningful work. It works such that if the network fully has all of the shards individually accounted for with workers, then the maximum issuance rate can be met. But if it can't, and workers are doing what I have referred to as multi-proofs, in other words, multiple shards within a single proof, then the issuance rate is actually lowered such that it follows essentially a square root. It's like an inverse square root rule. So, for example, if the network were at 102 Q per interval, and there were only enough workers such that 2 shards had to be covered for every single worker instead of 1 shard per worker, then you're dealing with 102 QUIL divided by the square root of 2. And so it's very easy for me to come to that conclusion when there is significantly more shards than there presently are workers today. So that's where I was coming from with that, and I hope that that makes more sense. Getting an exact estimate is never going to be perfect, but we have contributed a lot of documentation and charts necessary to construct a reasonable series of estimates on what it will actually look like, and that's where our estimates are coming from. Cool. So with that out of the way, I am going to jump in today's topic, and it's actually a continuation from the topic last time where I was walking through QConsole. And so there's a couple of things that I want to show today, and we're going to go ahead and start with a return to last week's demonstration. Let me move this out of the way and hopefully get things working without dealing with some weird chaos. It's always a little bit tricky. All right, and then I'll move this. I normally don't work with multiple monitors, and so that's partly where my difficulty comes from here. Okay, so we'll go ahead and pop this open, and we're gonna go to the QConsole site. So this is the onboarding experience, and I wanted to walk people through what that's like because this is actually a really strong reflection of what using the Quilibrium SDK for your own project is going to produce in terms of how onboarding experiences work. And so to start things off, even on the QConsole itself, dealing with the same type of infrastructure, we create an account, and it uses the same passkey style flows that people have already become familiar with Quorum and a few other things. I'll go ahead and hit continue, and it offers Touch ID as an option. I'm going to skip it for the sake of this demo, proceed without passkeys, and then it brings you to the next stage where you have to provide some information, and I'm just going to put in some test information. And now we have our account setup complete. So one of the things that I brought up in the last stream was how we utilize QStorage to do static web hosting. And I had a demo of that partially, but I didn't show the full end-to-end flow because it was running purely locally. We've since actually moved a whole bunch of stuff over to QStorage. All of the main Q assets have been migrated. We just need to do the total DNS flip. And so to demonstrate that, like if you go to www.qstorage.quilibrium.com, you end up with the Quilibrium website hosted on QStorage. And similarly with all the other assets. And we're going to do the DNS flip probably this evening. But the way that basically works is you create a bucket, and I'm going to go with, let's host the docs site. So we have the documentation for Quilibrium. It's a static page that's built using the tool Docosaurus. So I'm going to go ahead and do docs demo. And we're going to go ahead and hit create. And now we have a endpoint qstorage quilibrium.com/docs-demo. If we were to try to visit that right now, we would get the typical response of that not being allowed for there we go. Not being allowed for public usage because it's not been permitted. Originally, I had it set so that the defaults on buckets created on QConsole were public, and I quickly realized that the number of people that were going to run into issues with that, not being familiar with the nature of S3 buckets not being being public, being an issue would be well, quite a problem. So and now they are default non-public, but you can configure it. So I'm going to go ahead and set the website. The typical build that we use has a 404.html as our error document, and so that's what I'm going to use. So now we have the bucket configured. Obviously, if you actually try to go to it at the moment, it's not going to work, but because there's no files in it. But I'll go ahead and try to route it anyway. It's going to result in an issue, of course. And so let's go ahead and bring in all the docs. So going to have, just dropping a file over, very simple process, should be familiar for a lot of folks. And then if I recall correctly, yeah, the build's just going to be a bit recursive here. So I'm just going to drop over assets, and that's going to upload all the assets to QStorage. You can see that we got it very, very fast. And this is actually using the production QStorage APIs, even though that the QConsole instance I have right here is running localhost. And then bring in the docs folder. Whoops. And again, similarly, like it picks out the paths as you drag and drop them in. I don't know, do we have, yeah, we have some images. Okay. Drag the images over. And then the last two items, I'm going to drag the index.html and sitemap. And it's going to take a few moments to finish uploading. And now we have those uploaded. Okay, so now we have a full website that has been uploaded. So now that the website has been enabled, it is a public bucket. When we try to access it, we should get the docs. And so that's it. That's how simple it is to put a static website on Quilibrium. And this obviously is a much easier experience than I guess people might be familiar with when you're using Amazon or even Cloudflare's R2. We tried to make this as smooth of a process as possible for people who want to do the most basic things most quickly. However, like I said in the previous broadcast, the QStorage APIs are 100% compatible with the S3 APIs, minus like some very specific edge cases that like require Amazon infrastructure to work in the first place. But a lot of surprising things work as well. So if you have really complex business requirements that you weren't able to use like R2 for example, but you had to use S3 because of things like legal holds or object locks, we support them, and you're able to use it the same way you use the S3 APIs. All right. So that's basically the other things that I wanted to bring up about the buckets, and we'll go ahead and dive into the brand new stuff that I wanted to show today. So the nature of how QConsole works is you manage things in terms of either the raw services that you're interacting with to just get straight to the point of whatever it is that you're trying to launch, or if you have a more comprehensive project where you need to assemble a couple of resources and may require resources from other projects, you would construct a project. And so I'm going to create a simple test project. Give it a short identifier, and now you have a test project. Right now it obviously doesn't have a whole lot going on because we need to actually create some resources to use with it. So what I'm going to do through the series of steps here today, and I imagine we're probably going to, like looking at the time and knowing how long this will roughly take, I would estimate that we'll probably get about like 50% of the way through and have to carry on the next session. But what we're going to do with this test project is something that a lot of teams have wanted to know how to do in the first place, which is how do I launch a token on Q? And so we're gonna step through the process of launching a token on Q. And so now that we have this project, I'm going to go ahead and define a schema. So this is our schema editor. It should feel very right at home if you've ever used something like Visual Studio Code. It's a full syntax highlighted editor. It's actually using the Monaco editor from Visual Studio. And what we have here is like we just have a basic schema that we have basically as our template that people can just immediately jump off of. Obviously, you can use whatever you want, but we have a basic RDF schema that defines a token. And so I'm going to walk through a little bit on what the RDF syntax looks like, because there's a couple of different syntax varieties, and we're using the turtle syntax. So if you're not familiar with that, that would be important to understand. And then I'm going to dive into the specific types that are brought in related to QCL and overall the schema repository. So in RDF, you are defining a document schema that basically tells you how to relate over data. Or more specifically, you're defining instances of that data. We don't actually do that. We just define schema here. And the reason is because there's not going to be flat data that we incorporate through a schema itself. Instead, we're actually going to define that in code. But having these types is really valuable. If you read the white paper, one of the things that I mentioned in it is the notion of how RDF types are very efficiently mappable to overall hypergraph structures. And because of the nature of that mapping, you actually get implicit queryability for free. And so when you have types that are bound to RDF tuples, or triples actually, it becomes a very efficient way to self-index without having to define those indices yourself. So I talked about this a long time ago, so this might be a bit of a new concept for people who are just watching these streams recently. But one of the things I noted about the nature of a lot of Web3 protocols is that in those protocols, you end up having to build out a lot of boilerplate, and that's if you're willing to do it yourself. So a great example is, like, let's say I deployed an ERC20 on Ethereum. Great. Now, how do I ask who all has these ERC20s? Like, how do I know the addresses? How do I get the balances? How do I do anything to interact with this? And what ends up happening is you either have to write an indexer yourself, which is basically an application that will take the series of events that happen on Ethereum and then index them into a data structure that you can more efficiently query, or you end up paying to use a centralized indexer, which is what almost everybody does. And so this is actually one of the most profoundly centralizing aspects of most cryptocurrencies today, like most of the protocols themselves today, is that they don't have efficient self-indexing. And so by consequence, you end up having to rely on just a handful of parties, which really like devalues the whole purpose of a decentralized protocol. But I'm not meaning to cast shade. It's just the nature of the beast of something that was invented, quite a few years ago, and it's really hard once something is out there to make changes of it to actually adequately change and adapt and grow into providing those things natively at the protocol level. So what we did is we opted instead to use RDF as the basis for how types are defined on our network, because it becomes efficiently self-querying or self-indexing. And so that way you don't have to rely on a third-party index. You can talk to the protocol itself and you can get that data indexed efficiently. So here is our schema document. Like I said, it's a comprehensive boilerplate to launch a token, but I'm going to walk through all the details of this so that you can understand how to write a schema for a token, or really just anything in general. First thing I'm going to do real quick is I'm going to pop open another window because I know that like things are a bit weird. I'm running a stream on Twitch, I'm running a stream on Twitter, and I also am getting like chat messages from other sources as well. So trying to get like a holistic view on this, it's quite a hassle. Okay, cool. So we'll go ahead and, okay. So when we define a schema, the first thing you need to do is you need to have a base type that dictates like what all non-prefixed entities are going to be namespaced under. In this case, we default to the basic schema repository as our base. And then we have a few prefixes which are relatively standard. We define our RDF and RDF schema prefix as the given sources. And then there is a prefix of QCL. Basically, if you are writing an RDF schema that has nothing to do with tokens and you just like yeet all of that, you will need at least these 4 things. But we have a few more. And so when we're defining types, it's really helpful to individually categorize those types with a distinct namespace, especially if you're going to be having those types shared across multiple applications that might not necessarily use all of the types. So that way it creates less overload of what you have to import and what relationships are constructed. So in this case, we actually have a whole variety of different types that are constructed. So there's like an account prefix, coin prefix, pending, create, allow, so on. And all of these relate to the types that get created and the interactions that get created on the network itself. And so we're going to start with the most basic. The most basic, of course, is an account. So an account would have a lot of tokens. And the purpose of that is that you have a single unitary basis from which you can get some simple primitive data. So like, what does an account have? It has a balance. It has a public key. But the balance is going to be something that's a calculated property. It's something that we're going to continually update through interactions with coins. Why would we do that instead of a pure, like, just an account has a balance and we do all of our interactions based on that balance? Because that's actually what Ethereum does. The problem is, and this has actually been a real issue with Ethereum, is that when it comes to doing any sort of compliance-related concerns, you end up having an issue. Sorry, I got a spammer I'm going to try and get rid of if Twitch will let me do it. Cool. Anyway, so yeah, if you have a singular balance that represents all of your accounts, like coins, you have a compliance problem. So like, say for example, you have, you're a business, you have an account on a given network like Ethereum, and you are receiving tokens from a whole variety of different potential customers. Let's say that one of those customers is actually a sanctioned entity. In like your country, you can't do business with them, but because it's a permissionless network, they can just send you tokens and you can't do anything about it. In a case where tokens are individually like partitioned into discrete quantities that came from different individuals, that's fine. You just have something that is essentially stuck, frozen, don't interact with it, and you're done. But on Ethereum, everything's mixed together. So literally, the moment that a sanctioned entity sends you a token, you have had your account poisoned. And now you have to go through this long process to actually be in the clear when you want to actually use your funds. And so this is something really important to think about in terms of how you would design a token. So that's what we essentially did here, is we have a token as like a unit, a coin, separate from the account. We do have a balance, and that's for useful metadata, but the coin is the actual object that we're going to be dealing with. Okay, so with that in mind, we have an account. It is a class. If you're familiar with object-oriented programming, that should feel very familiar. And then we have this neat little attribute here called type. And type basically dictates to the QCL output that it generates what you're actually dealing with. Like, is this something that is a extrinsic that is stored on the network, on the hypergraph itself? Or, for example, is this something related to the actual execution of a method? So when you have types that you're storing on the network, type is extrinsic. When you have types that are being fed into as inputs of a method, you have a type of either garbler or evaluator. And I'll get into what that means when we actually start defining these methods. And on top of that, of course, we have a method. And so defining the method is literally just saying like, hey, for this type, it is an argument that goes into a function that we're going to call create transaction. And then we have some additional here of return. So you dictate like, this returns a update extrinsic output, an update extrinsic output, a create extrinsic output, and then finally bool. Every single method is going to at least return bool. But at a minimum, if you're going to be like messing with data on the hypergraph, you have a bunch of evaluative outputs. Like, is it going to update these? Is it going to create new ones? Is it going to delete? And then finally, we have the label, which is just useful documentation. It doesn't actually take any space. Okay. And then the next thing that we do is we define properties of the account. So we have total balance, which is a property of account. And then we choose domain, which is actually a standard term from RDF schema that is of a type called QCL uint, or unsigned integer. One thing that's important with types like unsigned integers, byte arrays, integers themselves, you have to define a size. And so in the case of dealing with integers, you're actually talking about like total bytes, like you're dealing with 32 bytes. Same thing with the byte array, you're dealing with 57 bytes for this. But what's important to understand is how that actually translates into QCL types. Is it's going to be turned into bits for unsigned integers, and then it's going to remain bytes for byte arrays. It's just an important note. And the last piece is the ordering. Ordering doesn't really matter in the same way that it does with other protocols like Ethereum, where you have to like come up with like clever byte packing ways to manage your types. You really don't have to worry about that. You just define the size and it slices accordingly. So we have the account, and then we have coin. Coin has the same type. It's an extrinsic. It lives on a hypergraph, has a balance. It's an unsigned integer that's 32 bytes. It appears first in the list. Another thing that's important to understand, I guess I didn't mention this, is the range property or attribute. Range is basically how you take a property and assign it to a class. And then we have the owner account, and we have lineage, and that's it. Like these three properties constitutes a coin. Now, let's say that somebody wants to actually send a coin. You create what is called a pending transaction. Because like I said before, one of the problems with protocols like Ethereum is that it's permissionless, such that if somebody sends you a coin, you can't refuse it. And worse, it's actually fully embedded with your overall account balance, which is really bad. But in the case of 2.1, we have what is called a pending transaction, which you can accept or reject. And it has a few components that are really useful. So the first is it has a to account, which dictates where this transaction is going. It has a refund account, which might not be the original sender if they wish to retain privacy. And then it also has what is called of coin, which is a reference to another coin. And one thing you'll notice is that unlike the QCL types, if the domain is one of the other extrinsic types that's been referenced, it will actually generate some different parameters in the method itself. And I'll get to that in a sec. Okay, and so now we have what is create transaction request. It is, of course, a class itself. And like I said earlier, it dictates that it is the garbler input. So there's two parties of every single method in QCL. One will either be one is always the garbler, one is always the evaluator, but sometimes the evaluator is just network, which is a default parameter, which means that there's no input from the evaluator side. And then there is the method name, which is create transaction, and that's how it is able to be separated in terms of namespacing versus what you will end up seeing in the generated QCL. It's important to note that. And like I said, if it does any sort of interactions that either create, update, delete data, then it will have a corresponding update or create, update, or delete extrinsic return type. And then also at the end, it must have a bool. And again, label just simply adds a helpful comment to define what this type is for. And the same thing here, you just have properties that are associated with it. So I could go through, sorry, losing my voice. I could go through all the different types that are involved in creating these, but I want to just like cover a couple of the highlights. So like I said, it creates a transaction, or when you create a transaction, you create a pending transaction. A pending transaction thus has to be accepted or rejected. And so naturally we have an accept request and a reject request. And those are the two inputs that will choose to accept or reject a pending transfer. And as you can see, the first argument is the pending transaction and a signature component. So yeah, without like getting too much more deep in the weeds with all this, one of the things you want to do when you're defining a schema, obviously, if you're not very familiar with RDF, you're going to want to validate it. And it does actually get pretty persnickety about things. Obviously, like basic syntax elements, like if you just are missing that, it'll tell you that it's missing that. But if you are missing something a little less obvious, like period at the end of a given attribute assignment, it will say that there's a problem there. But when you correct all those, you'll have schema as valid. And so we're going to create a schema called token, and this is the basic QUIL token schema as version of 1, create the schema, and now we have on our little devnet this token schema. And as I said, you can view it and validate, edit, etc., delete. Once it gets used, though, then it's locked, and you won't be able to edit it. You'll have to make a new version. You won't be able to delete it because there's now resources that are ascribed to it. And the next thing we do is write some code off of it. So this is going to be the bulk of what we're going to cover today, because I'm going to enumerate some of the very important differences between QCL and Golang, because historically I've just said, just write Go, and that's great, but there are some nuances to care about. So I'm going to go ahead and click token. It brings up this automatically generated QCL types. You can see them all here. And if you noticed, those methods that were defined on those given request payloads, those methods now appear as individual tabs here. So I'm going to go ahead and call this Bongo Cat. And now we have our created types. And there's a few things to note that are kind of important. There are some, basically some built-ins. So in traditional Golang, you need to have imports, and this does support imports, but there are some imports that are actually just default imported always, and that's, again, a key difference that I wanted to note. So, for example, dealing with the hypergraphs extrinsics, already imported for you, so you already have the basic hypergraph methods. You'll also notice that there's a lot of tags related here that help define some of those relationships. Because, of course, if you have a hypergraph extrinsic as your given type for this field, that's not helpful to the network to know which extrinsic it is. And so this helps define those relationships. And so we have our output types from our QCL, and then we have a series of marshallers. And so these are just like any other marshallers in Golang. They take data from raw bytes and unmarshal them, or they will take a given type and marshal them. And so that's important to know. Another thing that I want to note real quick, because the extrinsic object isn't self-documented here. The extrinsic has literally only one field. It's just the ref. And that is literally the address value where that given reference exists on the hypergraph. Okay, so that's great and all, but now we have our basic methods, including the marshallers. I forgot to show that. But how do we actually define them? So, like I said, generates a bunch of tabs. You can write this all out yourself and use the Q client to deploy this. But, obviously we built this tooling out to make it easier for people to launch a token. We are going to also add some, boilerplate templates. So if you just want to rip a schema and rip a token, say that you're doing a token schema and you want to just boilerplate out the methods, you don't care about anything other than, changing what the token name is. We're going to add support for that, but right now we just give you the basic shells of the methods that you need to fill out. And so I'm going to go ahead and fill them out. And so for accept, actually, I feel like accept is probably not the best flow to start with. Let's talk about transfers. Okay, so an accept flow, like I said, has a single garbler input and no corresponding evaluator. So it gets set to this default of relay, which is basically a parameter that says anyone can participate in this as a node. And then it has the corresponding outputs of hypergraph, update extrinsic, and create extrinsic. So we're going to go ahead and define that. And so the first thing you'll want to do is you'll need to interact with the hypergraph to retrieve that data. And so we already have some primitives that have been built for you to essentially request that data. So I'm going to go ahead and do a common pattern, which if you've written a lot of Golang in your life, you will feel right at home with this. And you can see that there's also suggested like a little bit of autocomplete. We're going to add more, but right now. So anyway, we're going to retrieve the extrinsic, and like I said, these objects that have an extrinsic property we have the given extrinsic labeled of coin, and we're going to go ahead and retrieve that. And then if there is no coin at that given address, we will continue to do the typical Golang salute. And then this is the important part. We end that with false. Because like I said, every method has to at least end in a Boolean value as the response type. And the reason is that this is how we can essentially tell the network, hey, everything that you've evaluated so far has terminated in failure. Like that's a way that we can assert that this request has failed. And it's basically like a singular bit that is put as the output wire that we can know that all the related changes that happened are null and void, and so we'll just skip it. Okay, and so once we have the coin in terms of bytes that we retrieve from the extrinsic, we need to actually extract it. So we have that unmarshal coin method, and we'll take the coin's bytes. And now this is actually like, so this code is coming from the Token Labs example, but you can still like define the raw size of the array, but you shouldn't have to do that anymore. We've gotten better at like taking the size of the inputs accordingly, but it's still useful to at least kind of like get you in the pattern of, you know, recognizing how much bytes are being used. And then we will take the account out of this data as well. And so we'll do hypergraph retrieve extrinsic coin owner account. And if it's not there, we do the same thing. So I'm going to save myself some time here. And then finally, if we have the account, great, we will take that and unmarshal the account. And it helps if I actually do that correctly. Cool. Similarly, like I mentioned before, it's not a requirement that you actually size the type. And then the next thing we're going to do is get the overall hash of these extrinsics. And I noticed that the screen is actually starting to get a little bit in the way of, or I'm starting to get a little bit in the way of that, so I'm going to resize this over. That should be good. Okay, and then, of course, if there's an error, notably error types, we don't have like a typical error type because that would be extra data that's unnecessary. So we just have our string responses, our error types that we use. But if there's an error, we're going to go ahead and return that. There is also, like, for debugging purposes, we do have a log facility where you can actually just write out, you know, log error and then the error itself. And then we verify. So one of the things that you may have noticed in the actual create transaction request is that we have a verify method and or a signature component in that given transaction request. And so we have this is what I previously mentioned with intrinsics, is that data types or like specific algorithms can be really expensive to do in MPC. If you're just like defaulting to garbled circuits, and one of those things is without a doubt signature verification. One of the things that we even did in the testing of the Bedlam compiler in Circuit Garbler just last week was a ED25519 signature, and that takes a much longer time than using a purpose-built algorithm. And so instead we're going to use the sign verify method instead of an MPC like baked into garbled circuits version of the verification method, because that would be much more expensive and we can do this more efficiently. So we have an intrinsic, is what we call them, that does the verification. So we'll do that and verify for that public key. that the given hash output and the given signature for that public key, and then set our domain, which in this case is just set to nothing, verifies. And if it doesn't verify, then it should be no surprise at all. We literally just return. Okay, and then last but not least, we create a new extrinsic, or not a new extrinsic, we get a reference to that extrinsic. This is diving, I guess, a little bit into the deep part of some of the like speed optimizations that you can make. I guess that's honestly not too important for right now, so I'll go ahead and skip that. So updated account, we create a new account structure, and it has a total balance of the current account's total balance minus the coin's total balance that has been sent. And then public key is set, of course, to the same account public key because we're just updating it. And that's how you update the account structure. You need to marshal it and then update the hypergraph. So we're going to do updated account bytes. And that is that marshal account method that was created in the QCL output here. And so we'll just do updated account. And then from there, we will create the extrinsic itself. So updated account ext, and that is the hypergraph update method that creates that entry. And so we have to type it out. Like I said, everything is strictly typed and it conforms to a given schema. This is partially how we enforce that. Note that these namespaces are all intrinsically bound to the given application namespace. So what that means basically is if you have multiple types that you are like doing from multiple different applications, there are some more advanced methods you'll need to use with the hypergraph, but like the default update, create, etc., that's going to all be scoped to within that application. Oh, right. And then, so we'll take the owner account reference, and then the updated account bytes. And then the next thing we're going to do is we're going to update the coin. So it's going to be the same entry as before, except the difference is going to be the owner is going to be set to nobody. So coin balance, and then owner account will be set to hypergraph empty, and the empty ref is basically saying that this is a null value, for lack of a better word. And then the lineage component, which is how we do MPC-based private set intersection of history without actually revealing the history of a coin. We update that accordingly using the Bloom intrinsic. And I need to actually do, I can use updated. No, actually I do need to do coin owner account ref. Yep, okay. And so that applies the given previous owner account to the lineage of that coin. And then we create updated coin bytes. And then create the extrinsic, same as we did with the account. That would be request of coin ref. And then finally the updated coin bytes. And then we will have a pending transaction that gets created. To accounts. So then we do the pending transaction bytes. Same thing, Marshall pending transaction. And then we follow, again, the outputs of that method, and so we return the updated account, updated coin, and pending transaction extrinsics, and then finally return true because it was successful. And that's it. That's how you create a method in QCL. And so, you know, obviously when you're designing something, especially as critical as a token itself, it's important to think through like the nuance of like what could go wrong, how could this be potentially hacked. So it is very important that when you're designing something like this that you take it slow. But obviously, like for things that aren't as super high security or super strict, like you can obviously write much faster. You can pull in code from other resources because again, it's still Golang, so you can import other packages. Okay. And then I guess the other thing I want to show real quick is kind of like what makes MPC so useful here is one of the things that MPC can do that like your basic protocols can't is like, let's say that I am, you know, I'm wanting to send you some QUIL tokens and you're wanting to receive said QUIL tokens, but neither of us actually wants to know who the other party is. And so in order to do that, obviously if you create a pending transaction, you have to know who the recipient is. The recipient might not know the sender, but the sender has to know the recipient. And so rather than create multiple legs of pending transactions so that you like masquerade who the recipient is ultimately, you can actually just use MPC to do that, and that's a lot more efficient. So we have this notion of a mutual transfer. And so we're going to go ahead and code that. Now, like our previous example, we have our ultimate outputs, but our garbler ends up, of course, on the left side, but the evaluator is an actual type this time, and that's the mutual transfer recipient request object. And so what I'm going to do is I'm going to actually like boilerplate out the stuff that we used from the last one. So obviously, like if there's anything wrong with the coin, like fetching it from the hypergraph, we have that. Otherwise, we unmarshal it and we carry on. Same thing with the owner account. We're going to go ahead and unmarshal that and carry on. Now, this is where it's interesting. We do the same thing for the destination account. But one thing that you need to understand that's different about what QCL is like versus programming in a traditional language, it is creating a garbled circuit for you behind the scenes. When you actually execute this code, you are creating a garbled circuit. And what that basically means is that it is a circuit, like a computational circuit, where the inputs are effectively private for each given side. So you are filling in the value as a sender and the recipient is filling in their value as the recipient, and neither party sees each other's inputs, despite this method being very transparent. So we have fetched the coin from the sender, we have fetched the account of that coin, we have fetched the destination account of the recipient, and all of those things are able to happen, and we're able to perform interactions mutually as two individuals in this equation without actually revealing any of those inputs to each other. And so, like before, we're going to create a hash here. I have a few things in the way on this screen, so I have to move it down. Extrinsics. Now, one thing that's notable here is, in this case, we need to change what we're hashing. Normally, when you're hashing data for like a proof that you know you have the key and you're permitting that data to be sent over, you would have more inputs to the signature. Like you would say, you know, I'm signing the coin's address and I'm signing who it's going to, and that's basically what we did in the previous one. But in this case, we don't know who the sender is, and we can't sign it interactively, because if we did, that would be incredibly expensive. So instead, we just have the signature up front as part of the request payload, and we only sign the recipient. Sorry, we sign the sender of coin. Like we get the reference of that and sign it. Okay. And then if there's an error, same thing as before. I'm actually going to copy and paste again because this is probably the most boring part. And then similarly for the recipient, we're going to do the same thing. And given the nature of streaming circuits, there's a certain order that you should do. So I'm going to like put it in that order here so that it's clearer. But what we want to do is we want to hash both of these so that the recipient proves they have the address and they have the right to like modify this. And then similarly, the owner of the coin is signing the coin that they have proof they have the right to modify this. And then we're going to do individual verifications. And so the first thing we're going to do is a basic verify of that sending account. And then we're going to similarly do a verification of the recipient account. And so we've done both of those things, but one thing I do want to actually point out real quick. Your circuit can get a little bit weird if you do it like this. You can actually get better performance if you strip that out and do it here. This also, like, given the nature of streaming circuits, this also is a little bit more defense in depth. Okay. And so then we have our same stuff that we did last time where we generated a bunch of boilerplate for the output extrinsics. So I'm just going to copy paste. And so what I've done here is I've created the updated sender account, the updated recipient account, and then the updated coin itself. And note that there's no pending transaction that gets created. So instead we just have 3 different updates that we're executing on the hypergraph. And then finally we return the updated sender account, extrinsic, the updated recipient account, extrinsic, and then the updated coin, extrinsic. And then of course true because it was correct. And that's it. And so that's how you define all of your methods. This is not available in the preview that I'm doing today, but we also generate the boilerplate for interacting with those methods using the JavaScript SDK wrapper. And so that's what we're actually going to dive into in the next broadcast because we're coming up on time. And so what that's going to be useful for us is that when we are basically closing the loop on this and we're creating a website where people can, obtain the token from like an airdrop or something, once you've deployed this and then you add it to your project, that SDK wrapper is being added to the project as a pluggable resource. And like I was talking about in the previous session about QStorage having pluggability as a supported thing, we have a template that lets you create a basic web page for importing that JS SDK wrapper and using it to basically create a token launchpad. And so that's the whole end-to-end flow, and that's what we'll get into in the next session. So given that we're up on time, we'll have to stop it here. But I wanted to take a moment to see if there's any questions anyone had while I was still streaming. Okay, doesn't look like there is at the moment. A couple things I also want to mention real quick as we're coming up into launch day. The stream the space that we normally do on like Wednesday/Thursday, depending on time zones, we're going to not do that this week because we're going to be fully heads down on getting 2.1 prepared for release signing and like any sort of final sanity checks around that to be ready for launch day. So just letting you know, we're not doing the stream this week, or the space this week. So if you do have questions in the interim, I am still like chronically online. I'm not necessarily chronically on Discord or chronically on Telegram, but I am chronically online. So if you do reach out to me, I will get back to you, and I'll be happy to answer any questions if you have any after the stream. But other than that, that's basically it that I wanted to cover for today. And like I said, next time we're going to cover the actual deployment process, the generated SDK, wiring that through with Q storage, and then if you wanted to have a, oh, I guess I didn't mention the Mint Authority. So if you wanted to have a dedicated Mint Authority for controlling the airdrop, wiring in QKMS and its SDK so that you can use MPC wallets to manage your airdrop distribution securely, and then just launching it as a website. So that's going to be the full end-to-end flow. Very excited to show the rest of that in the next stream. But until then, as always, glad to have you here and looking forward to the next one. All right, I will catch you all next time.